Welcome to this class on network analysis. In this class, we will solve some problems on initial conditions which we have been discussing for the past few lectures. So let's take the example of an RLC circuit. So the circuit is like this, where resistor R, an inductor L, and a capacitor C connected like this. The value of the voltage is 10 volts, the resistance is 10 ohms, inductance is 1 Henry, capacitance is 10 microfarad, VC0 initially is 0. You are required to find out I0 plus, di by dt is 0 plus, d square I by dt square 0 plus. Okay, so these are the three things that are required to be found. Okay, now let's see. This Vc equal to 0 means that the capacitor is initially uncharged. Okay, now what are we supposed to do? Like I said in the previous lecture, we replace the capacitor by a short circuit, and inductor we replace by an open circuit, right? So what is the value of current I0 plus after switching? This is the value of current after switching. Since the inductor is an open circuit, this I0 plus is simply going to be equal to 0 because no current is flowing. All right, so this is number one. This is found out. This I0 plus is with us now. What I'm going to do next is I'm going to apply KVL in this circuit, and I'll simply write that this minus V plus Ri plus L di by dt plus 1 by C integral I dt is equal to 0. And since I know that this term is representative of the voltage initially, right? So since we are told that this Vc0 plus is equal to 0, right? So this term is known to us, right? Now what will we do with this equation? We will simply say that at t equal to 0 plus, what does this equation reduce to? This equation reduces to R I0 plus L di 0 plus by dt, and this term is 0, so we remove this term, so this gets reduced to V. Okay, now this term is also, if you see, this is 0, so L di by dt is equal to V, and then you can say that this di by dt is V by L. Okay, so this is V by L. The value of V is 10 and L is 1, so this is going to be 10 volts. Since the term on the left hand side is current, this is going to be current per second. This is going to be 10 ampere per second, and you have to also write with this that this is equal to at t equal to 0 plus. This is very important. Now if you see, we have found out I 0 plus, and di by dt at 0 plus has also been found out. So what are we left with? We are left with the second derivative. So how will we calculate the second derivative? It's very straightforward. We simply go to this equation, which is our KVL equation, and simply differentiate it once. If I paste it over here, I will let me differentiate it once. So this will be r di by dt plus L d square I by dt square plus 1 over ci is equal to 0. Now this is known to us, this is known to us, so this we can find out. So if we rearrange these terms, what will I be left with? D square I by dt square is going to be equal to minus r by L di by dt. This is the general this is the general equation, general formula, general solution. Now since I'm interested in d square I by dt square at 0 plus, I can safely get rid of this. I don't need this. So what I will write, d square I at 0 plus divided by dt square is equal to minus r di by dt at 0 plus. So this is L is over here, and finally this d square I by dt square is minus r by L times di 0 plus by dt. So if we substitute the values, this comes out to be minus 100 ampere per second square. So this is the value of the double derivative of the current. Okay, so this is one example. Let's solve another example. This is number 2, and the circuit is like this shown here. We have a resistor R2 which connects the network like this. So this is the network. This is R2, this is R1, this is C1, this is L, this is C2, this is current I2 here, this is current I1 over here, and this is current I3 here. Fine. So let's see the conditions what is given to us. So it's given that steady state has been reached with K open. The switch K is open and steady state has been reached. Okay. At t equal to 0, K is closed. So the switch K is closed. Okay, so this is closed like this at t equal to 0. So we are required find initial values of all loop currents. we are required to find out I10 plus, I20 plus, and I30 plus. Okay, these three things are required. Now, how do we proceed? To proceed, we take a look at the circuit and see that before switching, what is the state of the circuit? Before switching, how will the current actually flow? Since steady state has been reached, what will be the flow of current? See, this capacitor C1 will be charged to some voltage C1, this capacitor will be charged to some voltage, and so will this C2 be charged. Okay, and this, there will be some voltage VC1 and VC2 present on these two capacitors, right? And they in effect will behave as this line will behave as an open circuit because there will be some voltage on the capacitor. So no current will flow through C1 and C2 initially, before switching, I mean. Okay, so what will be the how will the current actually flow? Let's see. So the current will actually take this path. This will be the this will be the path of the current. Since the inductor behaves as a short circuit in steady state, so before the switch action takes place, the current I1 will be IR1. If I write IR1 0 minus, this will also be equal to IL 0 minus, and what will this current actually be? This will be the voltage V divided by R1 plus R2, since there is no other circuit element present. And on the side we'll write at t equal to 0 minus, that is before switching. Okay, now if you take a look at the capacitors C1 and C2, these capacitors will be charged to some voltages VC1 and VC2. Okay, and since they are connected in series, what can we say about the current and the charge? We can say that the same current or the same charge flows, so we can say that Q1 is equal to Q2, and then we can say that C1 V1 is equal to C2 V2, right? So can we say that the total voltage across the capacitors, that is from this point to this point, or let me use another color, total voltage between point A and B, total voltage VC1 plus VC2, can I say that before switching, this VC1 plus VC2 is actually equal to R1 divided by R1 plus R2 times V? Just take a look and pause this for a moment and take a look at this, because if you see, before switching, this is a short. So what is the this R1 and R2 behave as a voltage divider? We have seen this in class. So potential difference between point A and B, what is the potential difference going to be? It is going to be this resistor R1 divided by the sum of resistors R1 and R2 multiplied by the resistance multiplied by the voltage V, that is the input voltage. So R1 and R2 are going to behave as a voltage divider, and the sum of the two voltages VC1 and VC2 is going to be the voltage division, like this. Okay, so now we know that the VC1 by VC2 is like this, C2 by C1. Okay, so we can find out using this relation, this equation number 1 and equation number 2, we can find out the values. Or to further simplify it, I'll just simply write d1 by d2 as well, where d1 is 1 over c1, which is known as the elastance, which we had discussed in class, if you remember, and d2 is equal to 1 over c2, right? So using this equation number 1 and 2, what do we get? We can get this relation, vc1 is r1 divided by r1 plus r2 times d1 over d1 plus d2 times v, and similarly vc2 will be equal to r1 divided by r1 plus r2 times d2 divided by d1 plus d2 times v. Okay, this is easy to show. You can just do some math and you will be easily be able to show this. Okay, so this is the voltage to which capacitors C1 and C2 will be charged before switching. Okay, always remember what is what switching instance you are trying to see. Okay, now after the switch has been closed and we are interested in finding out this I1 first. Let's start with this I1 first. This I1, if we apply just let me take a copy of this circuit over here. Let me erase the extra stuff. This is like this. This is C1. This is C2, this is I2, this is I3, this is K. Okay. Now, immediately after switching, if I take a look around this outer loop like this, what is my KVL equation going to look like? My KVL equation is going to be simply like minus V plus I1 R2 plus Vc1 plus Vc2 equal to 0. Okay. So I can say that I1 R2 is equal to V minus Vc1 minus Vc2. Okay, because the current because I am taking the outer loop into consideration. So if you substitute the values of Vc1 and Vc2 into this equation, you can simply say that I1 R2 is equal to R2 divided by R1 plus R2 times V. Okay, and then we can simply cancel out the two R2s and we can say that I1 at 0 plus is equal to V divided by R1 plus R2, and on the side we'll write at t equal to 0 plus. So this is known. This is I1 plus. Now if you take a look at the current I1, the current I3 and the current IL, what is the relation in between the two? I3 is the current in the loop and I1 is the current through the inductor only. Okay, so you have to make a distinction between the three. So if you see this I1 0 plus, and if you take out this I3 0 plus from the I1 current, you will get this value IL 0 plus. Okay, and this value is V divided by R1 plus R2 at t equal to 0 plus. And where do you get this equation from? Can you guess? Why? How do you derive? How do you derive these two equations? This is the current in the loop like this, and I1 is the current outside going outwards in the outer loop like this. Okay, so what is the current IL that is flowing like this? It is the subtraction of the two currents I1 and I3. Okay, so since this is known, it is known that the current IL in an inductor cannot change instantaneously. Right? What can we say? That if we compare this equation, let me call it A, with this equation B, if I compare these two, what do I get? I simply can make a comment that I3 0 plus is equal to 0. Okay, so we have found out the relation for two currents, I1 0 plus and I3 0 plus we have found out. Fine. Now we are left with finding the relationship for I2 0 plus. So how do we find out this I2 0 plus? For I2 0 plus, we can see the relationship between the currents I1 and I2. Okay, I1 and I2. So I can write this I1 0 plus minus I2 0 plus. What is this going to be equal to? This is going to be VC1 divided by R1. So I2 0 plus is going to be equal to I1 0 plus minus VC1 divided by R1. And if I plug in the values like this, I will simply be able to point out that it's equal to I2 0 plus is equal to this V divided by R1 plus R2 times D2 divided by D1 plus D2. So this is the value for the three currents. Now if you see this equation, you have to pay attention to how you derived this equation, and you also have to pay attention to how you derived this equation. So I will ask this in the class as to how you have come up with whether these equations are correct or not. I want you to take a good look at these two equations and see whether they are correct or not, and I'll ask students in the class about the validity of these equations. This equation in the red mark here and here. Okay, fine. So after this we come to the uh, end of this topic, this section. I would want you to complete more uh, unsolved problems given at the end of the chapter. Unsolved problems based on on similar logic, the way we have solved these problems before. You attempt at least problems 5.1 to 5.10 at the end of the book. Okay, so you should be able to do these problems. Okay, and I will ask students about the status of these problems as well. Okay, in the next lecture we will take up a new topic, that is higher order differential equations, and then we'll proceed in the completion of this unit. So thank you, and I'll see you in the next video.